Hi students, welcome back to the session on free vibration. So in this video, we're going to say about the free undamped vibration, that is the spring mass system. So how you going to find out the equation of equations for this kind of systems. So coming onto the spring mass system, you can see over there. So this is the spring mass system. So there won't be any damper involved in this case. So if you want to take a spring, so spring will not be initially the spring is not attached to a mass. So the spring has the stiffness K, so it is left as it is. So when I want to attach the mass to the spring over here, the spring will going to go for a expansion. So that expansion or elongation is going to denote as delta. So that will be the moment I want to get for the spring. So spring will start to expand. So that spring force will be K, that is the stiffness K is equals to F by delta. Or force will be equals to stiffness into the distance travel, that is delta. Whereas the weight of the mass, that is because it is acting due to the gravity, so it will be W is equals to M by G. So M by G should be equals to K delta, that is the force acting on that. So then you can say that the complete system, that is the spring mass system, is at a equilibrium position. So now I want to alter the equilibrium position by giving a displacement of x for the mass m. So I'm going to give a displacement x over here for the mass m. The mass m has been moved downwards. So I'm going to have W is equals to m into g. So there will be inertia force acting at the top. That is, it is always act away against the or opposite to the acceleration force. So the acceleration is given downwards. So the inertia force will be acting upwards. That is mx double dot. That will be acting upwards force. So I want to get mg will be cancelled with k delta. So I want to left with the kx. So mx double dot should be will be equals to minus kx, or mx double dot plus kx is equals to 0. That is the equation I want to get for a spring mass system. So this equations can be found out. That is the method of finding the actual frequency for a single degree freedom system can be done in three different methods. That is Newton's method, Albert's method, principle, or equilibrium method. So in this, what you're going to do is you're going to see the Newton's second law of motion, where the inertial force will be equals to the total force acting on the body, that is F is equals to m into A. Again, I'm going to go for the energy method. So energy method, you're going to go for law of conservation of energy, that is energy neither be created nor be destroyed. So where the total energy, that is the sum of the potential energy and kinetic energy, remains the same in a particular system. Rayleigh's method, that is maximum kinetic energy at the initial position will be equals to maximum potential energy at the final. So that is the three principles you're going to use for finding the natural frequency of a single degree of freedom of a free undamped vibration. When you go for the first method, Newton method, so I want to take a spring mass system as I explained the previous. So I have taken a mass, I'm going to take a spring with a stiffness K, mass as M, and X will be your displacement. So considering a spring mass system shown in the figure, so constrained to move in a rectilinear manner along the axis of the spring. So the spring constant stiffness is K, which is fixed at the one end of the mass M. So at its free end, I'm going to fix a mass M. The body is displaced from its equilibrium position vertically downwards. So that displacement is given by x. So this equilibrium position is called as a static equilibrium position. So after its displacement from the equilibrium position, it moves to a distance of x. So here we consider x is the positive, so in the downward direction. So I want to take the downward direction as a positive, I want to take that one as x. So considering the free body diagram, here you can take the diagram when only the mass is attached. So mg will be equals to k delta. So that will be the forces will be completely removed over there. So when I go for this side, so mg, so m into x double dot is acting, and k delta plus x is acting on the other side. So I want to take that condition. So in the equilibrium position, the forces acting on the masses are mg acting vertically downwards due to the mass m. So k delta is the vertical upward force due to deflection in the spring because of the load mg. So I want to take equilibrium position, that is this case, as mg will be equals to k delta. So delta is the static deflection of the spring. So since the mass is displaced from its equilibrium position by distance x, so then it is released. Therefore, after time t, the restoring force of a spring can be written as W minus k delta plus x. So I want to get as W minus k delta minus kx. So mg k delta is nothing but mg, that is a static equilibrium condition. So mg minus kx, I want to get as minus k into x as the equation of a restoring force. So coming on to accelerating force, that is m into a, so m multiplied by acceleration. So acceleration can be written as d square x by dt square, or you can say that one as x double dot. So equating 1 and 2 equation, the equation of motion of the body. So you saw that restoring force should be equal to the accelerating force. So the equation 1 and 2 gives us m into d square x by dt square will be equals to minus k by x. So when you go for this, so d square by dt square can be replaced as x double dot. So taking the kx onto the left hand side, I'm going to get as mx double dot plus kx will be equals to 0. So equation 3 is the fundamental equation of a simple harmonic motion. The solution of this can be given by x equals to a cos omega n into t plus b sin omega n into t. So since a and b are the constant which can be found out by considering the initial condition, and omega n is the circular frequency of a motion. So substituting the equation 4, this equation in equation 1, so I want to get, so this equation has minus omega square a cos n omega n plus b sin omega n into t plus k by n a cos omega n into t plus b sin omega n into t. So this I am going to replace in terms of x double dot x. So I am going to get as minus omega n square plus k by m equals to 0. So by taking the common, so this cannot be equals to 0. So it will be minus omega n square plus k by n should be equals to 0, or I can say that omega n is equals to root of k by m radians per second. So this is the equation I'm going to use to find the natural frequency using the Newton's method. So when you're going to find out the any problem is given, you're going to follow the same step, finding the inertia force, finding the forces acting on the body, that is restoring forces, then equating them, so you can easily find out the natural frequency of the system. So you're going to keep this one. So either you can write it one as x double dot plus omega n square into x equals to 0. So next video we're going to see about other two types, that is energy method and the Rayleigh's method of finding the natural frequency.